All right, good morning, everybody. Welcome to day 8 of the SAP, the final day. This is the start of the AM session. We appreciate you all hanging in here over the whole time. We have a very busy day today, so I won't spend much time recapping or talking. The few ideas that I had to share regarding how we're going to close the program out and give you credit and the plans for moving forward. We'll cover all of that in the blocks of time that we find free today. So no worry about that. And you've all received the schedule this morning, so hopefully you had the chance to look over that. So I'll spare you the details on the speakers, and they'll introduce themselves as they come on, and then we'll break, and then in the afternoon we have another full 2 hours planned out. So feel free to look over the schedule. And what I'll do, I'll go ahead right now and turn it over to Dr. Walter Lowe from Howard University. Sir, thank you very much for being here, and feel free to take it away.
Thank you so much, Dr. Sandifer. Um, First, I'd like to thank Kentucky State for inviting me. I had the great pleasure about a month ago actually being on campus for the first time. It's a beautiful campus, beautiful place, and I enjoyed being there, and I met a lot of people there. So let me start off by saying a little bit about Howard University. First of all, Howard University is located in Washington, D.C. It's an urban campus. We're about a mile from the White House. The main campus is about 250 acres. This year, we're going to have about 1,200 students. We're a full comprehensive university with graduate programs and undergraduate programs. I think we have about well over 1,000 graduate students, I believe, and that's across all the STEM areas, including our medical school. We have a medical school, excuse me, a medical school and a law school. The university is known for its alums. Some of our alums are Thurgood Marshall, the Supreme Court justice that actually argued the case of Brown versus Board of Education. I think I have that right. Um, Kamala Harris, Vice President Harris, is an alum of Howard University. Let's see here, I have a short list. Taraji Henson, the actress from Hidden Figures. Toni Morrison, the author. Roberta Flack. Sean Puffy Coombs, Puff Daddy, as you may know him. Ozzie Davis and Stokely Carmichael was an alum. And also Anthony Anderson of Blackish and Law and Order. So there's quite a distinguished list of people, and I left some out. But there's quite a list of distinguished alums from Howard University. So I'm a physicist. I'm in the physics department. I'm originally from North Carolina. I'm here in North Carolina now, watching the storm get started. And I grew up here, and I decided to study STEM. I guess I was about 12. I have a twin brother who's also a physicist. And so we both decided to study STEM. We were about 12. And we first decided on chemistry, and then we decided to move to physics because physics covered a little bit more of the fundamental sciences than does chemistry or biology or some of the other sciences. So what is physics? You can think of science, let's just talk about it in general. You can think of science as there's the science that deal with living things and the science that deal with everything else, sort of, or the non-living things. So physics is that science that deals with everything but living things. Now that's not quite true, because as you look at even living things on a very fundamental level, you start seeing the things that describes physics, such as charge transfer, and such. But for general, let's just say that physics is everything but living things. Now, one thing I wanted to talk to you guys about, and I see the last talk is going to speak to this, is how do you prepare? How do you prepare for STEM? Well, you have to start very early to prepare for STEM, because there's two things that you have to study very rigorously. and that's mathematics and science. Math is the language. Think of it as the language of science. So whenever you're doing science, you're speaking math. It's done in the language of math. So you have to get your, early on, you have to get your algebra, your geometry, your trigonometry, and hopefully some calculus. And that's even before you go to college. And then there are 24 other math areas, courses that you do once you get to college. Of course, you do more calculus, but you're expected as a STEM major to start with courses that contain calculus. So be sure to get your math and your science. So in science, if you have a physics course in your high school, then take it, but it's not, it won't kill you if you don't take physics in high school, but it will certainly help a lot. Uh, Now, essentially, all that's true for engineering too. So STEM, science, technology, engineering, and math. So that's going to be true if you intend to go into the technology or engineering areas also. Now, I'm what's called a condensed matter physicist. So what is a condensed matter physicist? Condensed matter. What is condensed matter? Well, physics, a more precise definition, is the study of matter and energy. So let's think about matter. What is matter? Matter is anything, going back to my high school physics, matter is anything that has weight or that has mass. So atoms are matter, and most things are made, well, everything is made up of atoms. So a condensed matter physicist is a physicist that studies a specific state of matter. Well, we all know about the states of matters, what liquids, gases, solids, plasmas. So in condensed matter, you have, let's say, a solid in which there's a special interaction within a solid that causes the atoms to have an attraction to one another that's not sort of your normal attraction. So in a abstract way, that's what condensed matter physics is. Now, condensed matter physics is the largest area, I believe to be the largest area of physics. There are more condensed matter physicists than any other physicists. So what I am interested in currently, and my interests change from decade to decade, I'm currently interested in renewable energy, and that's around an area called photovoltaics. And that deals with, well, photovoltaics are solar cells. And photovoltaic is the name of the effect of the physics that actually cause solar cells to produce electricity. Now, at Howard, I teach two courses. I teach an elementary course, which is a beginning course in physics. I have about 150 students typically in that course. And I also teach electrodynamics, which is an advanced course that deals with electricity and magnetism and how they relate. Now that is a sort of very advanced course, and I enjoyed teaching it because when I was a physics student, it was the hardest course I'd ever seen. And so I said, gee, I really want to teach this course because I don't see why it has to be so hard. Well, it's not hard, but it's challenging. It's very challenging. So if you decide to be a physics major, I can almost promise you that you'll find that course to be the most challenging in your curriculum. Now, a little bit about my background. I attended North Carolina A&T here in Greensboro, North Carolina. I went to college there. And after graduating from college, I went to graduate school. So I got my doctorate, a PhD at Stanford University in California. I might add that my twin brother did not, we attended A&T together, but we decided to go to different graduate schools. So I should say that he was less fortunate and had to go to MIT, but it's also a pretty good school. So he got a reasonable education also. So it's important that you are prepared for college, which will prepare you for graduate school, which will prepare you for work. My hobbies are computers. I teach coding in the summertime to students. And I might also add, in terms of preparation for STEM, no matter what area of STEM, or even not STEM, that you intend to become a professional in, it's imperative that you learn to code. So coding means writing computer programs. That's what we used to call it in the old days. So learn to code. Now, a good way to learn to code is learn a language called Python, Python. You just have to learn that if you're going to be in STEM. You have to learn to code. And I should also say that I'm an advocate of the Raspberry Pi. The Raspberry Pi, if you don't know about that, is a very shirt pocket sized computer for about $70. You get the whole thing, all the software is free. And so I teach coding using the Raspberry Pi. You can find it on Amazon. Just go to Amazon and type in Raspberry Pi. And if you have any questions that I don't get to today, please email me and I can give you more information about that. Now, what I would like to do is to just open the floor for questions. I'd like to have just you ask me things, and I'm going to ask you things, and we just talk at this point. So are there any comments or questions?
Yes, sir. I was just thinking as you were going, I was wondering where you see the greatest opportunity in the short term for students if they want to set their sights kind of on, a good model where they can be pursuing now. Where could they be looking at?
Although I'm trained in like really basic science, I am so excited about technologies and say applied sciences, the applications of science. And of course, computers. My two children are computer scientists. My son works for Google. So I think, and he's a coder. So he writes those little things, and his group writes those little things that move little cars around and those little pictures you click on. That's what his group does. He's not the only person doing that, of course, at Google. And my daughter is in cybersecurity. Um, her company provides security for the Coast Guard and such. So I think in the areas of cybersecurity, of course, there's a lot of talk about that right now. And I think in the area of energy, energy is sort of an abstract word, but all of our devices use energy. Everybody has a phone in their pocket that has a battery in it that you're always concerned about how many more minutes you have left and how many bars I got left and that sort of thing. So energy storage. So I think the future is in energy, an immediate future, immediate need is in energy research and people that know about energy that can work in energy, battery storage, energy storage, and in cybersecurity.
All right. Well, unfortunately, still we're actually short on the additional students. We have a couple that are really in the computer science area, and even one particularly young student that they're really hungry, and gaming and simulation is really where they're starting to focus on. So we have some really special people in our computer science department, and they kind of laid it out last week, the different areas, and they too were talking a lot about cybersecurity and then the systems, kind of the Internet of Things that's going to lay on top of the energy infrastructure moving forward. So I really appreciate you highlighting that. Uh, if you have any other final kind of closing thoughts, we're always just trying to point to where the opportunities are right away for the students to get involved, either to learn more or just to get motivated and inspired to chase things. Anything you could share about that?
Well, I would, in closing, I'd like to just say that it's important that you come from high school and you prepare yourself, even pre-high school, junior high, what we used to call it, in your math and your science, and that you do spend some time learning about the direction that you're heading. You become technology savvy, and coding is at the core of that. Even if you're not going into computer science, even if you're going to be a writer, you got to know how to code. That's just what you have to do. So what you have to know for the future. Wasn't true in my day, but it most definitely is true now because it gives you an analytical, procedural way of thinking. You have to be able to do that to code. And so even though you're not going to do computer science, it's important that you know how to do that. Um, and I would say to, when you decide on a college, um, do it deliberately. Don't just choose the college because it's near home, or find a college with a good program. And then as you go further than college to graduate school, look more discerningly at the specialties of the university, and choose from that group of universities. And I'd like to say thank you for the invitation today. And I look forward to seeing you guys out there in the professional world in the future as I sit for my rocking chair. And feel free to contact me if you have other questions about the university. I can direct them to people that can answer them more authoritatively, or I can tell you certainly more about our department. But thank you for inviting me and listening to me today.
Yes, sir. And thank you very much for being here. We really appreciate it, and have a very wonderful day. Thanks a lot.
Thank you so much.
My apologies, everyone there in the front. I did not realize that it wasn't capturing all the windows on my screen. So the kind of the front of that, I know I was just showing this, unfortunately. So, all right, so we are still short on the students. This is actually pretty close to our normal start time by the time we get everybody in here, but today seems particularly low. I tried to make sure I didn't have them blocked out. So in any case, we will continue on with the schedule as it's planned. We are recording this and posting it on a YouTube channel. So we have some students, they have other schedules and other things going on. So they come late and leave early, but they still get all the information through the videos, just no interaction. So it's less than ideal, but we'll continue moving forward. Next up on the schedule is Mr. Ed Wilcox. He's a watershed and research and extension associate, and the commander, I guess, of the Thoroughbred Research and Education vessel, this big boat that we have on the Kentucky River. And on the next to last day of our schedule next week, we'll be taking part and taking a ride on. Oh, it's there in his background there. So Ed, thank you very much also for being here today. Do you have some, do you have presentation slides or anything that I could share for you?
No, it's just a video I was going to do, a couple of videos, but they seem to have been corrupted and disappeared. So I'm kind of having to improvise here. So I apologize for anyone who may not see quite as much, but I got a model set up over here that is based on the program. Let's see, I got a pointer, you can kind of see that. And I'll just have to shift some of my models around to cover the same information that was going to be in the videos. And then I'll screen share so that you can see some visual aids as well when I get to those points. But yeah,
Okay.
I wasn't able to test this scenario out since I got into the Zoom right when everyone else did. So hopefully this all works out.
Yep. All right. Well, no problem there. Well, feel free to take it away and introduce who you are and what you want them to know. And thanks again.
All right. Thank you. So yeah, as Jeremy mentioned, my name is Ed Wilcox. I'm the Watershed Research and Extension Associate at Kentucky State University, and I'm also the vessel coordinator for the Kentucky River Thoroughbred, and that's the boat that's in my background here. It's a 50-foot houseboat, and it cruises along the Kentucky River in Pool 4 right around Frankfort. And and we're hoping that everything will be set. We're still getting the boat prepared, and we're hoping that it'll be set for y'all to cruise next week. But my presentation here today is very comparable to what I do on a lot of my presentations, and that is that I talk about how there's a correlation between land use and water quality. And so this model that I have over here, this is great for demonstrating that. And it's just a model of a watershed. And if you're not familiar with what a watershed is, it's a common drainage area. And what that means is that if it were to rain in the watershed, it all goes to the same place. But say like if it rains outside the watershed, it'll go to a different place. So for example, in this model, this yellow area is the Kentucky River watershed. And as you can see from the title on there, they can also be called catchments or basins. But if it were to rain and it were to rain in this yellow area, it would all eventually drain to one area, and that's up here near the top in a town called Carrollton, Kentucky. So that's just an example of a watershed, but also it's good to understand that smaller watersheds make up bigger watersheds. Like right here is the Red River, and right here is the Dix River. Each of those are their own little watersheds, but they make up the Kentucky River watershed. And where the Kentucky River drains is to the Ohio River, and that of course drains to the Mississippi River. So in that way we can see that say like the Red River or the Dix River is its own watershed, and that makes up the Kentucky River watershed. And then there's also the Ohio River watershed, and then the Mississippi River watershed, which is the largest watershed in North America. So those are just some examples of explaining how watersheds work. And we'll explore a little bit more about.
Yeah, I'm changing the spotlight to match. So whenever you want me to show your model, you can just let me know and I'll splash that on there.
All right, thank you. Okay, so so let's go on back to the model here, and we can talk about how land use affects water quality in watersheds. So this model is set up to be a demonstration watershed, and there's two watersheds or two streams that feed into this common area here. So there's a stream that comes down right there, and then there's a stream that comes in from over there. But they both lead down to this area, which would be the common drainage area for this watershed. And so like reality, this model is going to demonstrate a few things that happen in a watershed. So as we can see, we have roadways. And on those roadways, of course, there are vehicles that travel on them. So there's some demonstration of activity. And then it's just a matter of these cars don't drive for the sake of driving. They go to and from different places, usually from where people live to where people work. So let's go ahead and also put in some residential area here. And since I put that thing down, I took the trees out, but imagine that there were trees here before we put in the residential area, and those got wiped out for the sake of development. And then of course, residential areas need some infrastructure to support them, say like a water treatment plant. So this is going to be our water treatment plant. And then of course, all our residential area needs to be built of something like lumber or timber. And then there's concrete and other materials, copper, precious metals and such. And those things have to come from somewhere. So let's put in our resource extraction area here too. Perhaps it was timberland first, and then they decided to take the timber, and then maybe they're going to go for some coal underneath or other precious metals, because of course there needs to be some power for these people. And most of North America still gets its power from burning coal. So we can say that this will be our power plant over there. But that could actually be any industry or some kind of manufacturing segment or something like that, maybe, or a municipal resource. That could maybe be the drinking water intake or something like that. And of course, people need things to eat. So we got a farm over here. We got a couple of cows, but we also have a section of field here. So this particular farm, we'll say it has both livestock and horticulture operations. They'll grow crops. And some things that are missing from this model, but they still occur in many watersheds. There's transportation networks, so like airports and bus hubs and train stations, and then certainly things to repair those. So say like auto repair shops and or body shops and those sorts of things. But then there's also shopping plazas and such that are missing from this model. And just lots of different operations and things that occur in any regular watershed. So as we can see, we started out with a relatively plain area and we filled it up with all kinds of activity. Again, residential, resource extraction, municipal resources, manufacturing and industry, transportation, and agriculture, all going on in this model. In every single activity, it doesn't matter what we decide to do, but every single activity that we do is going to generate pollution. And I'm not sure if everyone's familiar with what pollution is, but if you're not familiar, pollution is anything that's in a place where it doesn't belong and it's harmful to that place. So for example, if we were to switch back over to the model here, we have a couple of vehicles that decide to collide. Maybe we have some auto parts strewn all over the road now and some fluids leaking out, gasoline and oil and coolant, all those sorts of things. All that's now spread out into the road, maybe running off the road and into the creek next to it. So in that case, the auto materials become pollutants to the environment because we're going to end up having some organisms that end up dying due to exposure to that material. So, but that's easy to think in terms of pollution as being something that's manufactured by people. But we can also say that there's abiotic factors to any environment. Those are the non-living factors that are in an environment. And one of those is temperature. So even heat can be a pollutant. And we affect that as people by the way we develop places. So for example, an urban area tends to absorb an awful lot of heat by structures getting warmed up by the sun and then radiating that heat off later. But that extra heat has changed the environment, and certain organisms may not be heat tolerant. So that heat has become a pollutant for that area and changed the environment, changed the ecology of that area. But so did the rest of the development as well. So certainly there's lots of things that people do when they alter an environment, how that's going to end up changing different features. But in our case here, the way we like to demonstrate pollution in this model is I use, and I'm a particular brand person, but I use, whoops, let's rotate it a little bit, hot cocoa mix. But if ever you decide to build your own model, which incidentally, this thing's kind of expensive. It's like $900. So certainly if you're looking to get into a good lucrative business, build and sell models. But in this model, the way I demonstrate pollution is hot cocoa mix. If you use your own model out of like a lid and trash bags and different things to create features, you could use any powdered drink mix. But I happen to like cocoa powder because it shows up really nice in the end product. But let's demonstrate how some pollution may get affected in this area. I'll just lay it down just to demonstrate that there's activity here, and that activity generates pollution. So I'm just laying down some pollution into the roadway. I'll go into a little more detail too, as far as what all this pollution maybe representing too. So let's put some down in the creek there too, because it's always ending up in the creek. We'll put some up here in the natural resource extraction area. All right, so now we have pollution, but let's go ahead and talk a little bit about each of the areas and how they contribute their pollution. So let's again go back to the vehicles. Again, the vehicles, as they operate, they're going to just leave fluids on the ground. You may see this in people's driveways or along roadways or in parking lots. There's the dark patches of fluid that have accumulated. That's oil or any other fluids that may be leaking out of the vehicle. But then as cars go through different places, maybe the operators decide to chuck litter out the window, or maybe they don't chuck it, but the wind just grabs it and pulls it out the window. I mean, certainly if you look on the sides of roads, you'll see plenty of material laying out there that had to have come from vehicles. So that's kind of what some of this is going to be representing. And then, of course, when we get into residential areas, we have people who like to beautify their surroundings. So maybe they put in gardens, and those could be just flower gardens, but they could also be vegetable gardens, and maybe they have both even. So, maybe they also want their grass to look as best they can. So maybe they have a yard service treatment or something like that. So we'll just put a big barrel here that's an indicator of fertilizers, because they are going to add some nutrients to their gardens to help make them grow. And then, of course, what they may also add, and here we'll put another barrel down, that's pesticides, because they want to make sure that their crops are protected from different pests, rodents or insects. It could be a lot of different things. But both pesticides and fertilizers are chemical additives to the environment. And certainly they're natural ingredients. A lot of the fertilizers are made up of nitrogen and phosphorus. And that occurs naturally in soil, but certainly people amend the soil to help the productivity. So, and then that can be in amounts that aren't natural, amounts and concentrations that are above what would occur in nature. But again, that's what we put in there to help our gardens grow and our grasses and crops even. And then again, the pesticides are there to combat critters that may also take advantage of all that smorgasbord for them. But and then to move from the residential area over to the farm is going to be very comparable, because in crops, they're going to be applying fertilizers and pesticides as well. And for the livestock operation, I just happen to have a couple of cows here, but livestock could be alpacas or chickens or hogs or llamas, any livestock, horses, not necessarily for eating, of course, but livestock are going to generate a lot of manure, a lot of waste. And then just to tie that back over to the residential area, there's a lot of homeowners who have pets, and they're going to generate pet waste. And any more farms are required to have a manure management plan, and residences or residential zones are required to have pet owners pick up after their pets. A lot of people typically only do that though once they're taking it for a walk. But they should even still be picking up after their pet in their own yards. But that doesn't necessarily happen. But anywho, so we have a bunch of pollutant additives that go in both residential and the farm areas that are fairly comparable. And then in this natural resource extraction area, as I mentioned, perhaps
what he's talking about is water
at one point. But to get at those natural resources, maybe they took out the trees. and that's going to increase soil exposure. And then that means that once it rains, once you have a rain event, that soil may get eroded and run downstream. And just different materials. Of course, there's all the machinery in there too that can be like vehicles and be leaking fluids and those sorts of things. And then as we have over here, as we mentioned, it's some kind of industry perhaps, and they have their parking lot where their employees park, and whatever they're doing is they do their manufacturing, they're going to generate waste. And that waste oftentimes can get discharged through a pipe, and that may go into a waterway. Say like in Kentucky, it's bourbon is pretty popular, so different distilleries will discharge wastewater, and that ends up going into local waterways and such. So as we can see, again, a lot of activity and a lot of pollution that gets released into the environment because of that activity. So, I mean, this just happens to be a green bottle, but it's a clear bottle, and you can see that the water is fairly clear. We'll just go ahead and squirt some in here too, so that you can see just right down there what it looks like once it collects and then gets pulled out. If I can get my little tray here out, it's still relatively clear, or it's still clear water. So now let's go ahead and make it start raining in our model, and we can see how this pollution then gets washed. And certainly bear in mind that this is just a model, and there's a lot of limitations that can be provided to models or by models. So while this is supposed to be an accurate representation of reality, there's certainly some things that get missed. And certainly this would be a very significant rain event for the amount of water to model size type ratio. But the idea is it rains in real life, and it's going to rain in this model's life. And a difference, though, in these models in reality is 100% of the surface here would be what's called impervious or impermeable, which means all the water just gets collected and then directed to a location. Whereas in the real world, the impervious surfaces are going to be like the roadways and roofs and parking lots and those sorts of things. And a lot of the water will actually soak into the ground. But again, that depends on the how developed the area is. And I'll demonstrate that with a visual aid. But anywho, so now we've had our rain event and the water kind of settled down into our common drainage area here. And our water that we're left with now looks like that. So that's a great demonstration of how our activity affects water quality. Certainly, it does require a rain event for all that pollution to get washed to that common drainage area or to just get moved around. But aside from water, it could also get moved by wind. For example, the litter on the sides of the road, sometimes that can get blown for quite a ways before it actually ends up in a waterway. But all of this is to demonstrate how our land use affects the water quality ultimately. Okay. And certainly there's ways that we can measure water quality. One of the ways that we can do that is through a device. This happens to be called a YSI Data Pro Plus. And this is a probe that measures a couple of parameters of water quality. I can measure temperature, dissolved oxygen, conductivity, and pH with this device. And those are just what would be considered chemical properties to the water. And there's a lot of other ones that can be measured, but that's all really that this thing can do. But otherwise, I can also try to measure the turbidity. And I can use what's called a Secchi disk. And this is an example of what a Secchi disk looks like. In this particular case, this is for a very mobile type operation. But what you do is you fill this tube with water, and then you look down the tube and try to compare what you can see down the tube to what's around the tube. And that's supposed to give you a turbidity reading. That's a very subjective way to determine turbidity. And it's better to use a mechanical device or a probe like the Data Pro Plus, so that way you can get rid of some of that subjectivity. I don't have a model of that out, but you could use a device called a photometer, and it measures the amount of light that's emitted versus the amount of light that's received to indicate how much stuff is in the water and how much stuff blocked the light. So lots of different ways that we can measure water quality. We're going to do some of that on the boat once we get to cruising, and you'll get to see how some of that ends up working. But other things that we can use to measure water quality, we can use, and this is where I'll try to start sharing my screen. We can use macroinvertebrates. And there's benthic macroinvertebrates, that just means, or aquatic benthic macroinvertebrates, I should say. Aquatic means that they live in the water. Benthic means that they live on the bottom, or they live on a, oops, it doesn't look like my screen's actually sharing here. Oh,
Yeah, we see it.
Okay.
We see it.
Benthic means that they live on the bottom, or at least on a surface underneath the top of the surface of the water. Macro means that they're big enough to see without any particular aid, like a microscope or anything like that. And invertebrate means that they have no backbone. So this diagram here shows some different benthic macroinvertebrates. This happens to group one are pollution intolerant, which means that they need excellent or good water quality. So as you can read here, there's some different examples. Riffle beetles, there's larvae and adults, flies, caddisflies, and there's some snails here. And this one happens to also be called a right-hand snail because of the way its shell opening is. And mayflies, all these are pollution intolerant organisms. And then group two, these organisms can live in a wide range. So they're somewhat pollution tolerant. That's going to be like dragonfly nymphs, crane flies. You can read the list there. And then there's also group three, which are the pollution tolerant organisms. And here's another snail, but this happens to be called a left-hand snail because of the side that its shell opens to. But midges and aquatic worms and such. And certainly this is a very limited list of organisms. And actually each list where they're in groups, it has to be calibrated to specific water areas or general areas to be effective. But this is an example of how we can use what are called bioindicators of water quality, and there's the living things. Other living things that can be used are different algae, and then also fish communities, because different fishes are more or less tolerant to pollution issues than others. Again, these are just bioindicators of water quality. So, and then we can also do, so far the two ways that we can measure water quality is the chemical side of it and then the biologic side of it. And then the last side of it is you can do habitat assessments. And that's one of the activities that we're going to do on the boat. And that pretty much means that you're going to look to see what's going on around the river and try to index the activity in the watershed or in the riparian habitat, and that's usually habitat that's right next to the waterway, to the water quality conditions. And so you never do a habitat assessment by itself. You always do it in conjunction with the chemical assessment or the biological assessment. The habitat assessment's never done by itself. All right, so those are different ways that you can measure water quality, and different combinations that you can end up using to make that assessment valid and useful. Now, and then of course, in order to make it scientifically valid, you need to have a quality assurance plan to make sure that you're not just grabbing, way out there data and saying that it's that, and then trying to use that data to make policy decisions or something like that. All right, so so that's how we can look at land use and pollution and water quality. And to back up though, because this is something that is really important, and is understanding the different sources of pollution. And let's go ahead and switch over to this image here. There's different sources of pollution that can pop up. In our model, we really only had one point source of pollution. That's one source of pollution. That's called
Hey, Ms. Wilcox, we still see the bugs.
Let's get rid of the bugs then. Okay. Okay, so there's two different points, or two different sources of pollution. One's the point source pollution, and in this image, that'll be listed by the city and industry. And that's where whenever they do whatever manufacturing or processing that they do, their waste is going to get discharged through a pipe, usually through a pipe. Although their solid waste ends up going to, say, like a landfill or something like that. So one source of pollution is called the point sources of pollution. And then the other source of pollution is called non-point source pollution, which is going to be the stormwater runoff from everywhere else. So as you can see, like these arrows coming off the construction site or off of the farms, and just off the terrain in the background there. And then there's runoff coming from the neighborhoods and the roads, and even shopping plazas and airports and those sorts of things. That's the non-point source pollution, stormwater runoff from everywhere that's not a point source. And to kind of put that into perspective, as far as like, well, how our nation is doing what it's doing to address pollution issues to waterways. Back in 1948, the Federal Water Pollution Control Act was enacted. And that wasn't even the first one, but it was meant to address pollution issues. And it wasn't until 1973 until a major revision came about, and that later became known as the Clean Water Act, because its purpose was to clean up the nation's waters. Or more specifically, its purpose was to make the nation's waters fishable and swimmable by the end of the 1980s. And the way they wanted to do that was by addressing the point sources of pollution, because that's where they saw the majority of pollution coming from. And so that required permits for dischargers. So they had to go through some kind of waste treatment before they could discharge their liquid waste into a waterway. And that did dramatically increase the water quality as far as it relates to water quality being affected by point sources of pollution. But ultimately, the nation's waters were not made fishable and swimmable because it didn't address the greater source of pollution, which is the non-point source pollution. So as far as why that happened, and if we can switch over to the model again, I put down, and actually I can quit screen sharing because I do have that.
Yep, then I can switch it over for you.
Yeah.
We see your handout. or your board.
Here we go. I'll just put it on the screen. I forgot I set that up. All right. But, so as far as why stormwater is such a big issue, and it's again related to development of an area. If we start in the upper left corner, we can see that, say, a natural area has 0 impervious surface, which isn't exactly true, because there's going to be some areas that maybe have stone or clay or something where the water doesn't exactly go through it very well. But the idea is if there's a 0 development area, you have a lot of natural areas that allow for infiltration. And as you can see, it says like 80 to 100% infiltration, but 0 to 20% runoff. And that may just due to the intensity of the rain event. If there's like a deluge, then too much water accumulates too quickly, and so it just runs off. It can't all infiltrate. And what's not mentioned in this image is the water that evaporates too, because some of it won't infiltrate or run off. It just evaporates and goes back into the air. But then if we were to go to the upper right corner where it says low density residential, and that could also be rural, so in agricultural areas. Well, we've increased the impervious surface to like 10 to 20%. So that's going to again be roofs and roads perhaps, but that can also start discussing soil compaction issues due to agriculture. Maybe the livestock are pounding down the ground, or repetitive heavy equipment operation compacts the soil to a degree where it's more likely to run off than infiltrate. But again, that depends on the amount of water that comes down in a rain event. But as you can see, we have reduced infiltration, increased runoff, because we have an increase in impervious surface. And in lower left corner, urban residential, again, increase in impervious surface, increase in runoff, decrease in infiltration. So that would be like a standard neighborhood. And as you can see now, there's also a pipe that's showing there, because a lot of residential areas end up accumulating stormwater in storm drains, and that ends up getting discharged to waterways, usually without any treatment. And then in the lower right corner, let's say we have commercial and industrial and urban areas. So now we have 75 to 100% impervious surface, 80 to 100% runoff, and 0 to 20% infiltration. So this is demonstrating how much extra water is collected and directed to waterways because of buildup and development in areas. And while this is a neat graphic and all, there's a model that we can use to demonstrate this. And so I'm just going to push this model back and bring forward.
Yeah, I cannot switch it over to your model unless you stop share.
I gotta stop sharing there, sorry. So what we're gonna do with this demonstration is this tray is supposed to represent an area, like another piece of watershed or something like that. And what we can do is try to mimic that graphic. And the way we're going to mimic that is we will increase the impervious surface by putting different sponges in resealable bags. And so as we go from development to development stage, we can measure about how much water is being absorbed or infiltrated and how much is running off. So I have it's listed as a 600 milliliter beaker here, but I'm only going to fill it up like 500 milliliters. Glug, glug, glug. Here we go. And so what we're going to do now is I am going to pour off this beaker. Oh, and just to say, these sponges have already been like pre-soaked once and emptied, so that way they don't just have excessive absorption and such. But we can pour off the beaker into these sponges and let it sit for just a moment. And then what we can do is try to pour off that which didn't get absorbed. I mean, and we can make it drain a little bit longer. But so out of 500 milliliters of water, I have about 100 milliliters of runoff or water that did not get absorbed. And so if you're into mathematics, which anybody doing science had better be into mathematics, there's going to be a lot of that along the way. But if you wanted to calculate a percentage, you can divide your final result by your starting amount. So we can divide 100 by 500 and then multiply that by 100 to get a percent. So in this case, we have like a 20% runoff. All right. And so let's go ahead and drain these sponges and then increase our impervious surface. I'll see if I was very efficient with my draining. Whoops, I got to be efficient with my pouring too. But I'll refill this back up to 500. All right, so let's go ahead and, oh, and just to say, if you guys wanted to do this little model at home as say like a project or something, a science project or whatever, it's just a disposable baking tray. It looks like a 14 by, maybe 14 by 10. And then these are just regular sponges, not the kind with the scrubby on the backside of it. And then these are just sandwich baggies and then a gallon, but you could also use quart if you decide to. Let's go and say that we've done the partial development, or maybe at the agriculture stage where we have about 25% increase in impervious surface. So let's increase our impervious surface by having our sponges get covered. And we can pour our water again into our sponges. And then see how much we recover from runoff. And so now I'm up to about 200 milliliters that I was able to collect. So we have another 20% increase in runoff. Oh, wait a second, that's not how you calculate percent increase. So, but anyway, we have an increase in runoff, a decrease in infiltration. And you can just keep repeating this until you see that you end up with 100% runoff. I'll go ahead and jump ahead to the 100% impervious surface, which to admit doesn't actually happen in most cities. There's still some sort of infiltration that happens even in cities. And bear in mind too that even in cities, you're going to have plenty of evaporation of water. All right, so we're back at 500 milliliters here. And as you can see, our water quality has diminished some because of the sponges. But the idea is that we can have our rain event. It lands on all our impervious surface. And then let's see how much we collect. All right. And so we're back to pretty much 100% runoff. We have about 500 milliliters there. There's just a little bit less, but okay. So that's a demonstration of impervious surface and how the runoff ends up being affected. So, but something that's not in this model is what happens in reality. And that is that people decide to make changes to their environment based on, well, that they've acknowledged that they've had some kind of an impact. So some things that we can do when we are living our lives and such, we can engage in what are called conservation behaviors. And some of those conservation behaviors may come from legislation, say like the Clean Water Act. But again, don't forget that the Clean Water Act focused on the point sources of pollution. And also the reason why it focused on the point sources of pollution is because it knew who those dischargers were. You could say, hey, this pipe belongs to you, company XYZ. But non-point source pollution is stormwater runoff, and it comes from a lot of places. And so you're not sure where that litter came from. You're not sure whose individual automobile leaked that fluid. Although it is relatively easy that if there happens to only be one livestock operation up a creek and you're getting E. coli or other pathogens coming down the creek, it's probably from that farm. But or other examples might be from construction sites where silt runs off the construction site. Those are examples where you can, it's still considered non-point source, but you have a pretty good idea who's responsible for it. But anymore, there's what are called best management practices, or and then even city ordinances to help address non-point issues. So for example, we can, if you notice in the model here, we show that the farmer has plowed all the way up to the water's edge. And so say like if there's a flood event that happens, that soil is going to get ripped out of there. So we can encourage the farmer to start using best management practices. So say like including a buffer strip between their cropland and their waterway. And this area would be called the riparian habitat, and that could be restored and create that buffer strip to reduce the erosion, that soil loss into the waterway. Then we can also engage in practices like contour plowing or pasture rotations for livestock, and even field rotation for agriculture or horticultural operations. And then even you can include buffer strips between row crops. There's all kinds of things that can be done. But yeah, we can do replantings of riparian habitats. We can put those trees back in areas that need them or that can use them, because as Jeremy mentioned, urban heat island effect, if we were to increase the shade in urban areas or even just change the color of the building, that will reduce the amount of heat that gets radiated or absorbed by the buildings and then radiated back out. In residential areas or in those riparian habitats, the root systems of vegetation tends to help hold things together. So that's a way that you can reduce some of the soil erosion. In construction sites or resource extraction sites, construction companies are now required to put in silt fences to try to catch that runoff and keep the soil from running off into a waterway. And then I don't know if you've noticed, but in new construction for, let's say, like a shopping plaza or even schools and those sorts of things, you may see a stormwater retention pond that's part of that construction project. So that stormwater that gets collected by the roofs and the roads and parking lots and all that, that ends up getting collected into a stormwater retention pond, which then can either allow it to infiltrate into the ground, or it can have a metered discharge, so it gets put back into a waterway without a flood event happening. So lots of different things that are in place now to help water quality issues and to reduce that stormwater runoff. City ordinances have been changed where people can disconnect their downspouts to the sewer system, because it used to be that the sewer system wouldn't wash out without that stormwater assistance. And so cities required people to have a rainwater coming off their roofs go into the storm sewer to help blow it out. But now ordinances, some ordinances have been lifted, and they allow people to collect their rainwater in rain barrels, or they can direct their water into rain gardens or swales. And all of those allow the water to get infiltrated back to the ground rather than just getting blown downstream. Because there's one of the things as far as the pollution goes that I didn't get to mention is that the greatest sources of pollution, a lot of people, or the greatest type of pollution out there, a lot of people tend to think that plastic's really bad, or even it could be the auto fluids and those sorts of things. But the two most common pollutants in the nation's waterways, not just Kentucky, ends up being soil and then bacterial pathogens from usually livestock operations. Those are the two biggest or most common pollutants in the nation's waterways. And you wouldn't necessarily think of soil as being a pollutant, but this kind of goes back to maybe we think of pollutants as being manufactured by humans or something like that. But soil tends to be high in nitrogen and phosphorus and nutrients, and those nutrients end up feeding aquatic plants like algae, and then you can end up with harmful algal blooms. And in those harmful algal blooms, eventually that algae is going to die, and there's other bacteria in the waterways that decompose that organic matter. They're aerobic bacteria, which means they live in the presence of oxygen and they breathe oxygen.
You took a shower?
Whoops, I'm sorry. Oh, but they use up more oxygen than the aquatic plants can generate. So that creates what's called a hypoxic environment or low oxygen environment. And things that need the oxygen, say like the fish and benthic macroinvertebrates and all the other critters that breathe, end up suffocating and dying. And that whole process, that explosion of life and then that massive die-off, that process is called eutrophication. And we often get to hear about that in the Gulf of Mexico. If you've ever heard of the dead zone in the Gulf of Mexico, that's one of the big ones. It used to be only a seasonal occurrence. Now the only seasonal thing about it is how big it is. But other places, if you ever check out Western Lake Erie, that still has harmful algal blooms and a eutrophication process that occurs on a regular basis. Not as bad as it used to be, but and then there's also the Chesapeake Bay and coastal Florida. Yeah, I don't know if anyone remembers hearing about the Army Corps of Engineers draining part of the Lake Okefenokee or something like that. But that caused a huge discharge of nutrients into the coast, into coastal waters, and it caused a red tide, which is that harmful algal bloom in coastal areas. And that caused a lot of die-off in aquatic life too. So lots of different, lots of different impacts that can occur, but then also lots of opportunities for us to make conservation decisions to help improve the water quality. Like we can restore riparian habitats, we can rotate our crops, even residential, because I happen to be focusing on agriculture, but as residential areas, we can make sure that we're properly disposing of our yard waste, and we can pick up after our pets, and we can make sure that we're properly storing and disposing of chemical wastes or any waste really. There's lots of different things that we can do. And I just wanted to point out, I'm going to screen share again. Oops, this is going to be part of your homework. Let's see. Well, I know, here we go. This is part of your homework that Jeremy is going to be handing out to you. This is a particular site called Green Match. It's out of Great Britain, and this happens to be like 70 ways to save the earth, but there's like 101 ways or 50 ways. There's lots of different pieces of information, different conservation behaviors, and me mentioning this particular site isn't necessarily an endorsement of the site. It just happens to be a site with a lot of different mentions in it. But I highly recommend that you check out these different conservation behaviors, but you can also check into NRCS's website and look into the EQIP program. If you happen to be a landowner with 10 or more acres, you can check into different government cost sharing programs for habitat restoration, or there's cost sharing programs, conservation lease, or what are they, easements that you can enter into lease agreements with, and those sorts of things. Of course, if none of you are landowners, you won't be able to do that, but certainly you can tell parents or guardians or neighbors or whoever about those sorts of opportunities. But lots of different things that we can do as individuals, and then also try to influence corporations in our communities who tend to have a much larger footprint than us as individuals, and a much larger impact. So certainly check out this as a resource. Otherwise, I would also recommend checking out, oops, I wanted to point out in the handout for your homework, one of the places that you're supposed to go is modelmywatershed.org. And I just wanted to do a quick demonstration of that. So if you had any questions, you can refer to the recording on this segment, or you can contact Jeremy or myself. And but once you get into Model My Watershed, you can click Get Started. And then for Delineate Watershed, well, we're not going to do that just yet because then they'll select a spot. But I'm going to zoom in to a church in Lexington. And they happen to be, oops, where are they? Not Newtown, on Russell Cave Road. Trying to find the, well, we'll just select this building right here and say, I'm going to delineate my watershed, select continental US medium resolution, unless you happen to be looking in Delaware, in which case I need to do Delaware high resolution. And then I can drop the pin and it will start calculating the watershed for that area. Certainly, it can only do so much. So if you click on a space where it can't recognize a watershed, it's going to select the next bigger watershed for where you clicked. But what it's going to show here is that this is part of this watershed right here called Town Branch. And this one happened to be easy. If you're not sure, whoops. If you're not sure which watershed you're in, you may need to use this other resource called the Water Health Portal. So watermaps.ky.gov/waterhealthportal. And that will take you into this area. And you can zoom into the same areas. And then you can find out which stream it is by clicking on the streams that show up in the area. I happen to be on Newtown here, looking into Town Branch. Well, I don't see it right offhand. I can't remember exactly where I clicked, but the idea is you may end up clicking on something that it doesn't show up initially. So you can look in here and try to see where the water is flowing to get to the next watershed. So in this northern part of Lexington, it's mostly in the Cane Run watershed. Let's go back to the water health portal. Whoops, model my watershed anyway. And if we were to follow Town Branch, it will eventually get into Cane Run or Elkhorn. Well, but that is just a way to help you see which watershed you've gotten into. Yeah, it looks like it's going to end up getting North Elkhorn. But otherwise, if we select our area again, something I don't know if you noticed it, but off to the left-hand side of the screen, it starts giving us these options here, these tabs. It starts talking about the streams, what order streams there are and what percentages are making it up. If you click on the land, it will give you land cover distribution. So here there happens to be a lot of pasture and hay. There's a lot of horse farms around Lexington. But you can also select soil and it gives you what type of infiltration you're going to get. And you can even click on animals to see what sort of livestock operations are going on. And you can click point sources to see if there's any point sources of flow into this area. And then if there happens to be any water quality data that's available, it'll show it up there as well. So those are just some of the resources that you'll need to look into when you do your homework that Jeremy's going to hand out to you after this program. I just wanted to demonstrate that.
Yeah, we
All right.
forwarded out the handouts just before. And I just want to draw the attention real quick. Yesterday, we kind of had a day that was all about geospatial. So we talked a lot about GIS and remote sensing and stuff. This application that you've shown is really precisely like the full bucket, right? This is an app where it's pre-selected data sets and it really just needs to know where are you interested in. And then after that, it
Right.
generates this analysis for you to be used. And this is really like exactly at the forefront of how the public is interacting with data, big or small. So, you know, the work is to put it in some kind of very usable format where a non-GIS scientist who's worried about something else can still take advantage of those tools. So thank you very much for sharing this tool.
Oh, you're welcome. Yeah, and does anyone have any questions or any comments or concerns about my demonstration or anything? I can answer any questions that folks may have.
Yeah, feel free to unmute yourself or to put any questions in the chat. And I guess I would just lead Mr. Wilcox and ask about, for folks that are getting ready to get near college or about to enter, where are the opportunities in the shorter term in kind of water quality? So in kind of that 5-6 year kind of area, where do you see being the real hot area in terms of water quality on behalf of the public?
For the last like 15 years, hydrology has been really big. And then it depends on how you approach that. A lot of hydrology minors or even majors tend to fall under geology majors, and then you specialize in hydrology or and then stormwater management tends to be a really big thing right now. And that's not likely to change within the next 10 years. So certainly hydrology or stormwater management. That's been really big for the last 15 years and is likely to continue. So that's kind of an educational avenue that you can take. Otherwise, if you're interested in any water quality issues, having a background in chemistry and biology, ecology, all of those will be very helpful. And if you're looking to be more of a generalist as opposed to a specialist, environmental science tends to be the educational pathway for the generalists. But there's banes and boons to most choices. So, and as a generalist, you maybe looked to do some specialized activity, but because of your general nature, you may be a little more limited in being able to perform that. So, but then again, as a specialist, you may be asked to do something that's a little outside of your expertise. And then as budgets go, they don't have anyone to hire for that, but you're the closest that they got. So there's lots of different banes and boons to any choice, but certainly hydrology with a focus in stormwater management has been really big.
Great. Thank you. Who is it that's in charge of policing the water quality for the public? Like who's watching that and responsible for responding to issues?
So on the national scale, that's going to be the EPA or the Environmental Protection Agency. However, they cannot monitor as much as they would like or enforce. And enforcement tends to end up being a whole separate area as opposed to the monitoring. So if you scale it down to a regional kind of thing, then you can say, well, there's ORSANCO, which is the Ohio River Valley Sanitation Commission. And they've been given jurisdiction by the EPA to try to monitor and enforce water quality issues and violations for the Ohio River watershed. And if anyone's ever heard of TVA or the Tennessee Valley Authority, that's something very similar, except it's for the Tennessee River system. So there's these regional consortiums that try to get together because watersheds don't care about political boundaries. They tend to be bigger than those, or they will say like a municipality may cover multiple watersheds, a county may cover multiple watersheds. So water issues tend to go beyond an individual location or like an arbitrary boundary like a municipality or a county or a state even. So that's why consortiums tend to work out a little bit better. But if you do get down to a state level, then in Kentucky, it's the Division of Water. Although Kentucky Department of Fish and Wildlife also tends to do some monitoring and some enforcement as well. But they tend to specialize in certain areas. And then once you get down into, county and even municipal divisions, they may end up having their own monitoring and enforcement capabilities that are still sanctioned by or ultimately sanctioned by the EPA or the federal government. So it all depends on which level or scale that you're looking at.
I appreciate you painting that picture there for it's very complicated and I see there's lots of opportunities for folks to just make something happen kind of in that citizen science area. So if you
Right.
see an issue, you can just kind of go about it. And that's really cool. Unless anybody else has any questions, if they want to unmute themselves or put it in the chat. My last question, and then you can answer that and then, feel free to kind of close out. If you could just kind of let us know, we've really been asking about how you ended up kind of where you are. So if you could think back to some point in the past where, I don't know if you've always been water quality, or maybe at one point you were going to do, be a doctor or something like that. But how did you kind of end up at the water quality type area? Just as a way to help students know that today what you're interested in doesn't have to reflect, where you're going to be, even in the medium term.
Right. So I'll go ahead and start back when I was in high school, because I want everyone to understand and hopefully not feel pressured too, because everyone's like, what are you going to do with your life? What are you going to do with your life? Well, when you're in high school, you can have all these dreams that you want, but the chances are you're not going to be where you're dreaming. So for example, when I was in high school, in my particular high school, was always trying to direct people to our local state college, which for me happened to be Northern Kentucky University. Well, our liaison for the university, our counselor, didn't really have a lot of information. So we got shown 6 degree opportunities. And so out of that list, I decided to pick law enforcement because I was like, none of the rest seemed to be that appealing. But then once I got to the university and I got to see a catalog and saw that there were way more than just 6 things I could do at that university, of all things, I decided to pick technical theater. So I decided to start out by making costumes and doing lighting for theatrical productions. Of course, then reality sets in, and this is where you learn what starving artists are about. Well, and I ended up not doing very well, so I took a little hiatus. I ended up joining the military, and found out that I was very interested in alternate cultures. And that turned into an interest in anthropology. So when I finally got out of the military and I went back to college, I changed my major to anthropology with a cultural emphasis. And then I also tended to focus on indigenous rights. Um, uh, but at the same time, I became involved with the Sierra Club, and I was also teaching people how to do like introduction to camping and or backpacking and those sorts of things. But I noticed that people weren't identifying with their place. And that I learned about place identity through my interest in indigenous cultures or in just in anthropology. And so I started to try to figure out, well, how can we help people identify with a place, develop a place identity and become connected to a place? Because you tend to notice that people who are more have that ownership of a place, that ownership is generally going to come from identifying with that place too. How to do that. So I got interested in indigenous education models, which then kind of turned me into an environmental where I ended up going with it was environmental studies, which are different than environmental science, because that tends to be like human environment interactions. But then environmental science is a great way to inform how, where you can better quantify some of those interactions and the impacts of those interactions. So I ended up going environmental studies and environmental education as my route. So even though I do science education and water science as a focus, I tend to distribute my information in terms of environmental education and environmental studies to help people understand how their relationship works. So that's how I ended up doing it. But if you're more interested in like being a project manager for like a habitat restoration or something like that, you're going to need some different avenues of approach. But the big thing to get away from or take away from my story is that, you know, I started law enforcement and ended up in environmental education and environmental science. And not that I ever actually wanted to be a police officer. It's just that that was, of the 6 options, that was the most appealing before I went to an orientation at the university. So yeah, it's but yeah, think of law enforcement's technical theater. It was way off. So
That's really wonderful to hear. I appreciate you sharing that. I'd like to talk more about some of those things actually. If no one else has a question, I'm going to go ahead and thank him and let him go. Mr. Wilcox, I very much appreciate your discussion. I really like that model. That was real cool. That was better than the slides for sure. And $900 too. I've been thinking about that. That would make an excellent little craft project, and we could fund everything on the sale of the models. So thank you very much, and have a great day, and thanks
All right.
again.
Thank you. Y'all take care.
All right. Well, that brings us toward the end, at the end actually of our scheduled AM session. If I could just kind of circle around before I let you go for the break. Well, first I'll say that we're going to be back at 1 o'clock, and this will be the last session. So we have two individuals that are. We've been a lot focused on skill development and STEM, and college and learning this and that, and we've been trying to allude that there's a lot other stuff going on in the world that is, certainly connected to education, but it's not all about learning to do stuff on the computer and all. And we have two people going to come on and share a lot of various things, and try to point out all these other adjacent areas that are awaiting you as you, continue to move forward. Um, but to close this AM session out, regarding how is it that you're going to complete the program and get, credit for having participated. And while we have 2 additional days scheduled for next week, they're really, kind of field trip oriented, and there's really not any new information like in the same way that there is here. And more than anything, that's a celebration and a reward to say thanks for, for being in my program for the last month. In order to take part of that, we need some way though to close out this class part. And as of right now, I have 4 people that have signed up and basically let me know very clearly what kind of project that they want to work on. So moving forward, we're about to figure out what that's going to look like, what the project's going to look like, and then what kind of a time frame. If you're not one of those 4 people and you want to do some kind of a project, we need to get it situated today, okay? But it's not a requirement to graduate from the program. Okay, it's just not. Participation in this online stuff is for us some of the most important for being here. So if you complete the evaluation, that's essentially going to survey you on your opinions and attitudes about the program. If you can complete that, that would be credit enough, and then you'll get a certificate of completion for the program. But I want to challenge you to work on the project. Okay, in the short term, there's no immediate prize for that, but it gets you started, especially for you folks that have graduated already and are going to be at the school in the fall. You could be well on your way to doing work, and by the time you hit campus, you'd be in an impressive state. Okay, and the doors will just open up. If you're highly motivated, the university will be highly motivated on your behalf, and I'll leave it at that. So, so if you're not sure about the project, and anything I'm saying isn't making sense, contact me right away. You can text me here during this lunch break, um, or call, or whatever you want to do. Any questions from the floor before I break? Feel free to unmute or drop anything in the chat. Okay, I only see a couple of private notes in the chat. We're going to be back at 1 o'clock. Going to be back at 1 o'clock. We're going to be at the same link. I'll keep this Zoom link will be open, and we'll be right back here at 1 p.m. to get started. So enjoy your break, and I hope to see everybody back for 1 o'clock.